Okay, we're live and live streaming. Oh, I've got the wrong thing on the VOU site, so let me fix that. Okay, I've got the right share on there. So sorry about, there you go. Nice of you to show up. So I think Jabber's in a canyon.
What's that?
I think you're in a canyon. Your background.
Good place for him.
Yeah, that's the first one I found when I was testing the feature.
Yep.
Oops. Right.
Yeah, and on the YouTube, we have Kurt's screen share, which is a good thing.
Oops. I noticed the chat window looks very different.
Jabber and I can be in the same canyon.
Okay.
I can always change that ring world thing that I have that I use in Zoom. If I can find the picture for that. I don't remember where it is.
Looks like a canyon I've flown in before.
Is that an uncanny valley?
I have no idea where that was from, actually. I found it on my email when I was testing out the. I should probably mute my camera while I'm having my dinner.
I just flew into the canyon.
Yes, you did.
Okay, we're still in the question and answer period, even though we're kind of quiet right now. So anybody wants to talk, go ahead and talk. Anyway, welcome to the Boston Linux and Unix user group monthly meeting. And I had the wrong YouTube share up on the website. I just fixed that. And check the YouTube is working. Although it's showing the Kurt's slide. And we'll start a little bit after 7. I think everybody's here that's going to be here.
Sounds good.
Just out of curiosity, does the chat appear on YouTube?
No.
Okay. So if I'm ever doing a meeting like this, we want to make sure to repeat the what was said in the chat if somebody's addressing it.
Yeah.
Yeah, I always copy and paste it in a text file and then post it on the blue website afterwards.
That provides archival of any guilty statements. But for responding live, it's always good to repeat the question.
Oh yeah, that's really true.
Yeah. Yeah, glad we didn't have chat rooms when I was in the military. I'd probably be in the brig. Or actually in the stockade, is what we call it in the Army.
Sticking with the space theme, did folks hear that this is the first time NASA's running Linux on Mars with their little copter that they flew? Red Hat did an event, I think, last week, touching on it.
That's great.
Different modified version of Linux.
See if I can find a link.
I just posted the link on the chat. And it's on the BLU main page too.
Was it Red Hat, Elliot, that they were running?
I don't think so. I'm looking. They didn't mention a specific distro. It may be a very, very customized install.
I would think Magna.
It's on GitHub, though. Yeah, I've got a link here.
Woohoo!
If you can build your own little Mars copter, you can run this.
I wonder if they're looking for helicopter pilots.
I think with the latency, it's always autonomous from this day forth.
The latency would drive you crazy, Jerry.
Have you ever flown a Hiller? Hiller helicopters have a 270-degree latency.
Yes, but the 4 to 12 minutes is a bit more than 270 degrees.
I was talking about flying up to Mars and doing it myself.
Well, that would give you some latency on this meeting.
That is correct.
for one-way tickets, I think you got to talk to Mr. Nikolai Musk.
I'm not sure he's promising a return either.
That's what I said. For one-way tickets, you got to talk to him.
Yeah, they got to go buy a roadster first. That's the only ones he's sending out.
NASA's sort of committed to two-way tickets.
Yep.
I heard that
Narrow-minded.
NASA's helicopter on Mars has a flight time of about like a minute or a minute and a half, and then it has to spend the rest of the day charging by solar panels and into a tiny battery. And it was a really tight optimization problem of being able to actually do anything useful with it versus being able to keep the battery charged and not overload the system with too much battery weight.
I think it's more of a proof of concept what they have out there right now to see if.
Yeah, it's a proof of concept, and it
Yep.
did what they said it was going to do. But it's also a useful tool that it can fly, it can hop a little every day, and it can
Yes.
explore around where the mother vehicle is.
Yeah. Yeah, helicopters tend to be fairly complex because you have, in that one you've got two concurrent rotors, one on top of each other. That way you don't get torque.
Yeah.
Like you do in a regular helicopter where you have tail rotor and all that kind of crap.
The only helicopter design crazier than an electric helicopter I've heard of was somebody was supposedly working on a steam-powered helicopter drone late last century, and it was just, you got to be kidding me.
Well, we still make electricity with steam engines. They're not useless.
They're not useless, but they don't tend to come in light.
Batteries aren't light either, but they made it work.
Yeah, the technical term for lightweight steam engine is shrapnel.
Yeah. But, helicopters are very complex to fly because you're in a regular helicopter, your rotor blades act as a gyroscope. And so when all your controls are set 90 degrees ahead of the plane of rotation. So, you get that. And that's why I mentioned Hiller, because Hiller used aerodynamic instead of hydraulics, they used aerodynamics. And so anything you did with the I get auto muted by my earphones. So just got muted. So the Hillers, it was my first training helicopter, but everything you do, has that delay built in. In any case, we can start the meeting, Kurt, anytime you want to.
Sure. And if I get knocked off the air, I'll just let Elliot take over since he's probably going to be the one I pass to anyhow. Or Dave Cayley has a couple of probably some slides or something to tell us too. So, and then we'll end up at the student presentation. I don't think we're going to get another speaker tonight unless we have some lightning presentations. We were going to have a guy talk, but it looks like he's going to join us in May now. I'll work that out with Jabber. All right, so let me give you a little bit of a background on the student cluster contest and why the Boston teams have been going to it pretty much consistently for the last
Kurt,
50 years or so.
do you have two microphones going?
No.
Are you using two laptops? Still just
No,
one?
no.
Yeah.
Yeah.
You're fine now. You were coming through really weird.
Okay.
Sounds
So
good
the
now.
first year, okay, so IEEE Supercomputing is a big, it's the biggest IEEE conference and it moves around the country. SCO8 was in Austin, and this was the first year that they did the student cluster contest. So because it was in Austin, we sent a proposal with Dell as our sponsor and worked out really well. The night before the conference started, they had a new SKU come out, and we swapped out all the old processors with the new processors, or AMD. I'm thinking, was this Barcelona or before Barcelona? So that the timing worked out well. We got in there the day of the conference and swapped out the processors. Got a slightly better system competed that year. And then, like I say, on and off for the last couple of years, we've fielded pretty much a team or multiple teams representing Boston schools. In 2013, we had 5 local schools in the standard track and 2 in the commodity track. So Northeastern and Bentley participated. They had 2 tracks that year. They ended up getting rid of the commodity track. That was one where you had to keep the budget down. Each contest has a cap on the power, but this particular contest had a cap on the budget as well. So 17 and 2018 had a very heavy UMass representation on the teams that we fielded. You might recognize a couple of guys from that picture. I think Evan presented at BLU a couple of years ago on what the UMass teams were doing for their competition that year. If you want to go to the student cluster contest site, there's a lot more pictures. I think we have pretty much all of the students that have competed all over the last decade and a half up there. So here's how we usually try to figure out how to compete. As far as an optimization problem goes, and I'll let the students talk more in depth on this, it's not all that complex. We know we have a 3,000 watt cap, and after that, we get to make most of the design decisions. We can optimize for CPU-centric codes or memory-bound codes or embarrassingly parallel codes that might have an accelerator that we stick into our PCI bus. These are all certainly things we can look at to build a 3,000 watt cluster to then bring to the contest, hook up to their power supplies, and then run through the roughly 3-day competition. So the gear is mostly on for the full 72 hours. This year, we're going to have to come up with our generic solve with these 2 additional codes that we have to look at. Last year, they had different codes. They changed the codes up every year. They do try to keep an embarrassingly parallel code in there, and then maybe something else that stresses something else out in the OSI 7-layer stack. If sometimes we get something that's heavy on a stream or maybe a fast Fourier transform or something. So we always have the benchmarks. Linpack scales up and scales out. Conjugate gradient, that's very much somewhat CPU centric. You can't really hot rod that one too much by selection of your libraries. And the IO 100, we'll talk about that more. The students will definitely talk about what they've done in previous years on that. There are a couple of other student cluster contests. There's something new this year called the Winter Classic going on right now. I don't know if we have someone from the Winter Classic online now. I sent an email out to some of the other traditional student cluster contest universities, so we may have some other teams join us. The Asian Supercomputing Conference, we've been to that twice, mostly BU students. It's in a city that moves around in China. The year I went, it was in a big university town that was about a 4-hour flight from Beijing. It was really pretty far inland. The HPC Advisory Council runs the one in Frankfurt at the International Supercomputing Conference. There's some lectures on that coming up this week and next if you wanted to look at that at the agenda site. Northeastern, BU, and UMass teams have gone to that competition. That's a really difficult to get gear over there. You almost have to partner with another couple of schools, couple of really big schools, or find a local company to partner with. We partnered one year. We went over there. We partnered with Cavium, which is another Massachusetts company. They had a partner in Germany, so there was gear waiting for us when we got over there. It's really quite tricky to get your servers over to Germany. We've looked at that a couple of different ways, and partnering with a European company is the way to go. And then that last link there, Dell Technologies is having a podference this next week, and I just discovered that. I actually heard they advertise on WEEI during the Red Sox game, so that's how I found that one today. Now I'll pass this off probably to Dave Cayley because he only has he has a couple of minutes to talk too, and then Elliot's got the most slides of all of us, other than the students probably. But folks, if you have additional supercomputing topics or student cluster contest topics, feel free to chime in. We're going to have some time at the end. I have some more slides. I'm going to see if I can get them working on my other laptop. But let me pass that back off to Elliot or Dave.
Yeah, I'll be happy to take it. Let's see. I guess this is the one. How does that look?
Looks good.
Okay, let me just go like this. So I just wanted to, this is an interesting meeting for this discussion. Recently, Northeastern, Boston University, and Tufts put together a project with the state of Massachusetts called the AI Jumpstart Cluster. This was in response to a call from the state for helping Massachusetts companies sort of take the next step in AI and machine learning and apply it to industrial problems. And the enabler here was parallel computing. So we acquired a $2 million cluster through the grant through the John Adams Innovation Institute, Mass Tech Collaborative. And again, this is to provide that sort of, there's also included with this is our funds for supporting consulting by university faculty and students with the Massachusetts companies leveraging this hardware. So, the PyTorch TensorFlow world will be brought to Massachusetts companies and the capabilities of some very nice hardware. So again, we're using GPUs and some nice network connectivity. And I'm happy to say that Microwave was the prime vendor. Thank you, Elliot, for all your patience and thoughtful everything you did. So just a little bit about the system. It's got 7, what at the time were state-of-the-art NVIDIA DGX A100 systems capable of 5 petaflops on deep learning. 14 nodes of AMD CPU, GPU, heterogeneous computing platforms. They have, each node has 8 MI50s. We were pushing for the MI100s, but they weren't available at the time. We're hopefully going to be moving some of those out and moving in MI100s as AMD is able to get more quantities. And again, they have got some nice, half and single precision as well as double precision floating point numbers. There's a large memory node, and we're also integrating this with the DARPA 5G Coliseum simulator. Basically, that's a large-scale parallel system, mainly FPGAs. That basically you can configure any 5G waveform simulation and do all kinds of research on it. So, and we're combining, AI machine learning processing with the 5G work. So that's what I wanted to share today. It's a pretty exciting project. I believe we powered on just the rest of the AMD nodes this week. The NVIDIA nodes have been up, and so happy to report on this in the future. But some exciting stuff. Nice to have very fast hardware.
Dave, is there a rolling schedule for industry to request access?
So there's basically going to be in June a workshop. It's going to be held online that basically will feature Massachusetts companies are invited to that. We're really trying to target medium and small companies. And the idea is that that's getting to know you. We're going to be the faculty will be there talking about their capabilities, and the companies will be listening and trying, and what they will be doing over June, July is putting together short white paper proposals where the state will provide the funding for the consultants to work with the companies. And the idea is to get the project started with this initial investment. And, we're going to see where it goes. But we're very encouraged. We've had, other projects like this with the state that have been very, very successful. And Northeastern's well positioned, given its co-op program and its, use-inspired research model. Other questions? You can go to the state website. Go look at the AI Jumpstart. I probably should have put up that on the slides, but I can put that on the chat later. Thanks for the opportunity to present.
Hey Dave, can you send me a copy of the slides to put on the Blue website?
Sure. Who's asking for that?
John Abreu.
I can send it to, if you pop up, I'm not sure what your address is, your email address.
Oh, it's jabber@blue.org.
Jabber at
BLU.org.
Okay, got it.
Oh, it's JABR.
Okay.
Okay, thanks.
Yeah, no problem. Oh, it looks like you're up.
Yeah, okay. Let me see if it'll let me share. Thanks, Dave. Okay, and I guess Kurt was right. I do have more slides. I'll try and take not too much time here. Oh. And it's giving me a big red box. Can you see my screen though?
Yes. Yes.
Okay, good. Okay, I'll just go. Okay, and for those who don't know me, I work in HPC, mostly with, I guess what you would say, traditional server equipment. So I'm not doing anything too esoteric.
Hold on, Eric.
Elliot, your screen's blank.
Oh, crud. Huh. Try it again. It says that it's sharing my screen.
Yeah, it's there now.
Ah, okay.
That's good.
Okay. Let me know if it goes black again. So I'm going to share some fairly standard HPC equipment that has been announced in the last couple of weeks. A lot of major vendors have been releasing new products. I'll start with AMD. AMD EPYC is AMD's x86 CPU for servers, and it's a couple of years into this product now, and they're definitely seeing good performance and good adoption in the industry. So there were a number of years where AMD didn't really have a competitive x86 server product, and it it really affected the whole ecosystem and the whole industry. There just wasn't competition. So this is their third gen, so they're calling it Zen 3. So they're iterating on this design. Let's see if this picture doesn't really do it justice. Their design is interesting in that they're taking multiple chiplets and putting them onto the CPU. So it gives them it's a different kind of economy when you're binning things. If you don't have to make a gigantic 800 square millimeter die and make sure that it's perfect, they can take these little dies and put them together. So they get a lot of advantages. They get a lot of cores. These things go up to 64 cores, up to 128 threads per socket. And really, this was just an iteration. So their Milan third gen 7003 series has pretty much all the benefits you can see on the left side here. 8 memory channels of 3200 megahertz memory, up to 64 cores, as I said. And the real difference in this generation is microarchitectural improvements. So they're seeing 20 to 40% improvement in instructions retired per clock cycle. And they also improved the L3 cache. So in the top right, you can see it was in previous gen, it was 2 16 meg L3 caches. And then the bottom right, you'll see it's now 32 megs of L3. So it's better performance, particularly for some apps that can really leverage L3. Maybe not even something that's well threaded, that's only using a few cores, but a lot of cache. So they have a couple of models that take advantage of that. And they pushed on the clock speeds as well, because that was still one of their disadvantages, that they had tons of cores. They've had 64 cores for a few years now, but the clock speeds were lower. This is an eye chart, I know, and you don't have to look through it. You can reference it later. I'll share the slides. But again, these and this is not the whole SKU stack either. This is just mostly the 64 core and 32 core SKUs. At the bottom, you'll see the frequency optimized SKUs, where they're pushing 3 to 4 gigahertz, which was their weakness in past gens. If you look, where's the wattage? The wattage is right down the center. Things are getting hot, and it's not just that. You'll see throughout this deck, everything is hot. So these are CPUs that are taking 200 or closer to 300 watts each, and that is just the standard in the industry now. So it's different, and some new challenges, to be sure.
It's an infrared flood lamp.
Yeah. Oh goodness. I guess it speaks a little bit to the success that we've had in successfully cooling them. It wasn't that long ago that more than 100 watts was a little bit odd for a CPU, and a little bit of pushing the envelope. And now we're easily double that or closer to triple that. It's really impressive. And I guess as long as we keep them cool, they're going to keep pushing it on CPUs and GPUs as well, really. Yeah, I'll come back to that. But so that continues. So AMD really has the lead on, well, maybe I should say had the lead. They had high memory bandwidth, high core counts, and Intel didn't have an answer to some of that. But Intel just, I think 2 weeks ago now, launched their new, it also happens to be their third gen, which they call Ice Lake. And again, these are for servers. You'll see a few of these products in workstations, but anything you see in a laptop or low-end desktop is going to have some other iteration of these chips, like maybe a similar microarchitecture, but a different design, and probably not a 300-watt chip in most cases. So this is Intel's architecture. They're matching AMD EPYC now in 8 channels of 8 memory channels per CPU socket. which is particularly important for high performance computing. You'll see systems struggle. It's always a bottleneck getting data to the cores. They improved the links between the CPUs, the UPI that you see in the center there, and everyone now, well, I should say most everyone is running PCI Gen 4. So AMD EPYC has Gen 4 PCI Express, Intel Xeon has Gen 4 PCI Express, which is double the bandwidth of previous generations. So you can push 25, 26 gigabytes per second to a GPU or to a high-speed network device at this point. It's impressive. Though, of course, it still pales in comparison to some of the other bandwidths. If you look at the typical bandwidths between some of the GPUs, AMD has Infinity and NVIDIA has NVLink, where they're pushing hundreds of gigabytes a second between the devices. So PCI Express still pales in comparison to some of those specialized links. And then, this is all of the new SKUs. It's a lot. I don't even think it's. I won't dig into it here. I'll highlight a few in the next slide. But you'll see that the whole right-hand side is specialized SKUs for particular VMs or for hyperscalers. The people that are trying to build something like a Google or a Microsoft. Some of them are liquid-cooled specific. Some of them are for networking. So we're starting to see more of this, where you can't just get the one best CPU. They're really tuning it to a particular workload. A lot of the stuff on the right there is not even guaranteed to run at the specs posted unless you're running the particular workload that they've optimized it for. So that happened in the past gen, but it's more and more with every generation. And here's the few that are most likely to be of interest to the compute-focused folks. On the right-hand side, on the top, that's the liquid. It's designed for liquid cool. So that will probably be the SKU that goes into some of the big HPC systems. And then there's single socket optimized also on the right. And then on the left is the kind of mostly core count focused. You can see, 32 cores, 40 cores. They top out at 40 cores. So AMD still has the advantage on core count, with AMD going up to 64. And again, kind of towards the center, you'll see wattages. And most of the SKUs in this line are 200 watts or more. So not so different from AMD, where it's, AMD goes with 280, Intel's going to 270 watts. It's a lot of heat. It's a lot to exhaust. And it's a balance now. Everything is a balance between power and clock speed and core count. If you let these things overheat or run warm, the core counts will suffer. I'm sorry, the clock speeds will suffer. And the clock speed even varies based on the instructions you're running. Like if you're doing a vectorized instruction, an AVX2 or an AVX512, there's a whole different set of clock speeds for those instructions versus the clock speeds that are shown here. So they do have high wattage, but they also behave differently depending on what your workload is. And that's just, again, every product in the industry is doing that at this point. And then NVIDIA just had their event last week, with still a little bit going this week. They put on a really good event in that everything is online. So you can see the links here, or just Google NVIDIA GTC. There's hundreds of things. There's so much to learn, and it's pretty inspiring and very educational as well. I wanted to highlight one in particular, since we're all still fighting COVID here. There's a really good presentation from a few different folks talking about their COVID research. And I just want to kind of give an idea of the scale of things, the big and the small. So the world's second largest supercomputer is Summit. It's in Oak Ridge, Tennessee, at Oak Ridge National Lab, and it was one of the supercomputers used for COVID research. The COVID virus has 305 million atoms. If you're simulating just one COVID virus, virion, I think they're called. But even on the second largest supercomputer in the world, they can simulate 64 to 128 nanoseconds per day. So that's taking the one virus protein, seeing how it's shaped, seeing how it behaves, and they can get what works out to just a fraction of a fraction of a fraction of a second. So they can see how it moves, on nanosecond scales. But the problem is that via some other earlier SARS research, they've established that it usually takes a few minutes like with the original SARS virus, it took 10 minutes for the virus to enter a cell. So how do you see what's happening over a minute, multi-minute time scale when all you can simulate is just a handful of nanoseconds using the largest supercomputers available? So you can dig more into what they found here and the different methods they're combining to achieve this. But it's very impressive what science was able to accomplish in 12 months. But it's also humbling to see just in some ways how little we're able to accomplish even with these impressive systems. And they did announce some new products as well, and I'll jump through that quick. But I wanted to point out that it's increasingly common, again, to that point of specialization. In the old days, if you saw a GPU from NVIDIA, they were all kind of based on the same chip. They all kind of had the same capabilities, but that is no longer the case. And there are specialized, and that's not specific to NVIDIA. Most vendors have multiple chips now they're designing, and you have to know which one you're aiming for. So the one on the left is the one used in the DGXs, for example, the ones that Northeastern has in the AI Jumpstart cluster. And those are really built for, I don't know what you want to say, 50% AI, 50% HPC. You can see they've got separate int, floating point, and tensor core units. And they're really only going to be in servers and DGX systems. If you're trying to put them in a workstation, there's almost no options except for the workstation that NVIDIA makes. Whereas on the right side, you'll see tons of these in workstations. This is the GeForce that no one can buy right now, GeForce 3080 or 3090. And it's got a mix of floating point units, tensor core units, and the ray tracing cores. But you can see that although these are not to scale, they're allocating different real estate to these different designs. So the units on the right have better floating point performance for like a single precision FP32, and the units on the left can't manage the same FP32 rates, but they can run more tensor operations per second. So you really have to know what your workload is doing, and if you're building a general purpose system, then you still have to kind of balance your workloads and figure out what the ideal choice is going to be, or mix it, right? Again, heterogeneous clusters are kind of the norm now, with different mixed units and different types of systems for the different jobs. So they announced a couple of specialized units. The one on the left is based on this architecture shown on the left, and the one on the right is based on the right. Although there are big hot GPUs, NVIDIA's hottest GPU is 400 watts. These are slightly more power efficient. So the one on the left is under 200 watts, but outperforms NVIDIA's last generation at 250 or 300 watts. So you can get the big thing that's 400 watts and super fast. You can get the thing that's a little more modest, but still beats the previous generation. And the other big news, and I didn't put a photo of the Queen in here, but NVIDIA is trying to acquire ARM, and the UK has officially announced now that they're going to be reviewing that. But whether the acquisition goes through or not, they are working together, NVIDIA and ARM. And I pulled this from their website about what they think it's going to bring to the world. I think a lot of people asked why NVIDIA was acquiring ARM, because ARM licenses its IP. So you don't have to own ARM to build an ARM product, ARM-based product. And NVIDIA's already announced that they're going to be doing that. So we're going to see NVIDIA products with an ARM CPU and an NVIDIA GPU. And in fact, a lot of their embedded stuff already has that, right? If you've got a Jetson or have seen a Jetson, it's already doing that kind of thing. And you can get a dev kit of the new gear. So confusingly enough, Ampere is the name of the company that's building these chips. And this summer, you'll be able to get servers that have server ARM CPUs, a proper ARM CPU for a server with NVIDIA's latest architecture of GPU. Then you'll also see this DPU thing, which is a new interesting way to think about data centers. I'll mention in a minute. This is NVIDIA's software stack for ARM. It's basically just a mirror of their software stack for x86. But the point being, you can build a very good HPC system on ARM CPUs, GPU or not, right, at this point. But if you do want a GPU, the software stack is there for you. And this is their This is their DPU. This was announced last year, but now it's time to really get serious and start thinking about what this is going to enable. And in fact, Red Hat CTO spoke at GTC about what he thinks this type of DPU can do for a data center. And that was very interesting. I recommend that session. At a high level, this is the process. If you think about it, so you can see on the right, it's a network card that has a processor in it, and essentially the argument is you're going to have bad actors in your systems wherever they are, right, in the cloud or on-prem, and the recommendation is that you basically build your infrastructure and your services around these DPUs. The DPU is kind of the trusted part of the network. If you can do a trusted boot on the DPU on this network device with a built-in processor, then the argument is you don't have to trust your host, and kind of everything within the server itself is under the control of this network device. I'm still wrapping my head around it, to be honest, but it's an interesting way to think about it, and we'll see if this really does do things differently. So you have to think about this as a network card that runs Linux separate from the Linux that's in your host operating system. And honestly, a lot of servers are already running Linux on their BMCs. So you like the management chip on the server is running Linux. And then now your network card device is running Linux, as well as the host also running Linux. It's a lot of different things to wrap your head around, for me at least. And this is the software stack, DOCA, which is data center infrastructure on a chip. So this is the stack that would be running on your network device, separate from the host. And you'll be able to start buying these devices soon. You know, they were kind of announced last year. It was hard to get your hands on them, but you can actually buy them now if you want to deploy this. And although the dev kit that's shown is with ARM, it's going to be supported on x86 as well. So it will be very interesting to see what people end up doing with this. And then finally, for a point of discussion that I thought was interesting, I don't know if you folks have already covered this, but one of the people in the HPC community mentioned that now that Oracle lost their suit to Google and you cannot copyright an API, are we going to see direct CUDA implementations? So AMD already has a thing where you can kind of do like a find and replace on NVIDIA's GPU software stack, and you replace CUDA with HIP, and then you can run a code that you wrote for an NVIDIA GPU on an AMD GPU. But I guess the argument now is there's no need for find and replace. You can just implement NVIDIA's API, and you should be in the clear. I am not a lawyer, but it's an interesting argument. There's probably some other applications of this as well. And that's all I had. Comments or questions?
Kaustubh, you've done a lot with HIP and Boltzmann and things like that, haven't you? Can you tell us if HIP eats 20% of your performance, or is it worth it?
Who are you asking?
Kaustubh.
Oh, we're actually doing HIP. We're working very closely with AMD. We're actually writing a book on HIP right now. And no, you're not going to eat 20%.
Oh, good. Because as you might know, getting discrete NVIDIA cards is pretty tough to do these days.
Understand.
It really is. Although I will say, I didn't mention at the top, but there are shortages all over the industry.
Oh, yeah.
GPU or CPU or power supplies, like just any component is shocking. And I've heard that the steel they use to make the chassis is 3 times more expensive than it was a year ago. It's just a mess.
Dave, can you run CUDA on CPUs?
No.
Okay.
Can we run HIP on CPUs? Yes.
Okay. And you don't take much of a penalty there either?
I haven't looked at.
Okay. All right. Well, will your book come out before November?
Yes, I think that's the target.
Excellent.
Yes.
That's a harder compare, though, right? That's an unfair compare because like an NVIDIA GPU is similar compute performance wise to an AMD GPU, but then when you're comparing it to a CPU, it's have to have a little more nuance.
Yeah, it's like comparing MATLAB to C++. Yeah. Just don't do it.
Hey, Elliot, do you know much about these companies that they basically have solid state motherboards like Cerebras? I mean, it looks like a motherboard, but it's 5 nines pure silicon. I mean, is that going to be the future of HPC someday?
Well, I mean, I haven't touched this myself, right? And I know some of the folks on here might be. I don't know, is VJ on here? But if the product from Cerebras always costs $1 to $5 million, then there's certainly a role for some other architecture. Many of the people I talk to on a daily basis don't have $1 million for a supercomputer, so that does kind of pigeonhole it.
Come on.
Yeah, there used to be a space for specialized supercomputers, like EMU wanted to do graph. Convey and Convex wanted to do graph machines, and now there's no specialized supercomputing company unless EMU is still around, but that's pretty much the only. Silicon Graphics is gone. I can't think anybody else that was in a separate space rather than.
Is Cerebras specialized? I mean, I think they're trying to sell to any AI use case, which is still pretty broad.
Well, their sales pitch was, what can you run on 1,000 CPUs, right? On a SOC. So if you wanted embarrassingly parallel CPU only codes, that may have a 5-year or a 10-year plan, but I don't know. They're not the only company that has talked about doing it that way. I think they're the only company with product, but there's some research efforts that are going that direction.
And the last time I had spoken to them, they aren't quite there yet with graph workloads like SparseGem or even graph convolutional networks. Because of the irregular memory accesses. So maybe machine learning and dense workloads, but they're still struggling with graph.
Yeah. Yeah, I saw that ARM v9 was announced last week as well, and I'm not sure why ARM didn't do this in conjunction with NVIDIA. But they had a bunch of product release videos come out last week or the week before.
And I think they're a real contender, right? I mean, I guess we'll see. But we've had a few folks try to ship ARM servers and then fail. Is that 2 or 3 times now? But maybe this is the time that it really moves forward. I guess HPE has already been having success. But a lot of the smaller players didn't make it.
All right, should we hand it over to the students?
Yeah.
All right, sounds good. Give me 1 second, and I'll share my screen.
Hey Ben, can you hear me okay?
Yep, can you?
Yep.
All right, let me know if you can see this.
Yeah, I can see.
Yep.
Yeah, it looks good.
Yep.
Go green team.
All right, great. So hello, everyone. My name is Benjamin, and I am the captain of the Massachusetts Green Team, as well as the president of the HPC Club here at Boston University. This year, we are hoping to compete at the SC21 Student Cluster Competition. I'm joined by my fellow teammate, Howie.
Hey everyone, I'm also a student at Bobby, and I'm in charge of the benchmarking for the team, and I'm happy to be here today.
Okay, so let's get started with a little bit of an introduction to the history of the team. So the Massachusetts Green Team, the Boston Green Team, just the Green Team, whatever you would like to call it, is a cluster competition team formed as a collaboration of students from colleges in the Boston area. And in the annals of the history recorded by the Boston University High Performance Computing Club, we can kind of trace the formation of the team back to around 2011. with Team Chowda, who competed at SC11 and SC12. They actually achieved the second place ranking, and they ran a cluster of NVIDIA Tesla K10s, which, unbelievably to someone like me who has only recently just gotten started with interacting with these systems, was pretty cutting edge at the time. So in the following years, the team went on to compete at many competitions with varying university representation each year. From what I found on website archives, this would have been an average of about one competition per semester or so. And in the red jackets here is one iteration of the UMass team, and in the blue jackets is the BU and UMass joint team. And many of the students on these teams were recurring competitors year over year. After 2018, though, things just kind of stopped and the team split up. The HPC club at Boston University was still submitting competition applications, but we weren't able to compete again until just last year at SC20, and we were still a standalone Boston University team. But hopefully all that changes today. As part of my last year as an undergraduate, I wanted to do something special for this team's competition, and that was to revive the Massachusetts Green Team. Both Howie and I personally had really great experiences at SC20, and as soon as that competition ended, we started planning on how we could bring back the spirit of cooperation amongst the universities. So a little quick introduction to familiarize everyone with the team members. David is a junior at Boston College studying computer science. Throughout his undergraduate career, he's become really familiar with operating systems. And he hopes that by competing in the competition, he'll be able to bridge a gap in his knowledge by working on different types of file system structures. He will also be the first person to represent BC at the student cluster competition, which is pretty exciting. Carlton is a sophomore studying computer engineering at Boston University. This summer, he's going to be doing research on computer processor cooling solutions, and he wants to learn more about how HPC can be applied to his research. Richard, who's actually in the call today, is a junior at UMass Lowell studying computer engineering. Because of his integrated coursework, Richard has a pretty deep understanding of circuits and electromagnetics, and he hopes to gain experience working with computational science in order to better understand the capabilities of computers. Howie is a sophomore at Boston University studying computer science. He competed in the competition last year where he led benchmarking, and he'll be doing the same this year while also helping out with the other applications as well. Howie currently leverages cluster computing as a researcher working on deep learning techniques for medical imaging. Michael is a freshman studying computer science at BU as well. He's pretty relatively new to high performance computing, but he's considering HPC as an academic career path because he enjoys optimizing algorithms for hardware. By attending the competition, Michael hopes to learn more about the field and connect with industry professionals. And finally, I am a junior at Boston University studying ECE. Since this is my last year participating, I hope that the team will do well and will be able to create a lasting partnership with everyone involved. So a little bit more on to what Kurt mentioned earlier in today's meeting. The Student Cluster Competition is a multi-day event held in early November as part of the Supercomputing Conference. The competition sees international representation from all over the world as students come to represent their universities. There are 6 students per team. Everyone is going to be an undergraduate, and there are about 16 to 18 teams in total each year. Our task is to build a supercomputing cluster and run 3 benchmarks and 3 to 4 applications on it, as well as reproduce scores from a paper submitted to the conference. These benchmarks are going to test all aspects of our cluster, including graphics performance and I/O bandwidth. And our challenge is to optimize each workload to achieve the highest score amongst everyone competing. And this competition is a really good opportunity for students to learn about HPC, as well as network with industry professionals, and everyone on the team is excited to be a part of it. So like I said before, Howie and I attended last year's competition as part of the BU HPC club, and we wanted to share some of what we learned from it. So SC20 was an online event, and we got some great experience working with Microsoft Azure. We ran a second generation AMD EPYC system as well as a NVIDIA V100 system. And one great thing is that we were able to do a lot of benchmark testing with multiple VM SKUs. However, we couldn't get most of the applications to run. In LinPack, we scored 65 teraflops, HPCG just shy of 600 gigaflops, and 0.7 in IO 500, an IO bandwidth benchmark. And we were also able to submit every part of the mystery application. So looking back, we spent a lot of time during the competition getting benchmarks set up. Each time we started up a fresh VM, we would need to go through the installation process over again from the start. So having scripts for each of these would have given us more time to work on the applications. And additionally, we learned that we should really be submitting something for everything, even if it's not completely finished. That bottom image right there shows the applications that we submitted. And you can see that we only did something in one category. That was that mystery application I was touching on earlier. And all the others, we could not submit anything. So that's one aspect we need to work on. Additionally, we need to better distribute our system resources to each of our workloads, or else we might end up starving them. For this year's competition, we're hoping to represent Boston on location in St. Louis. We'll be tackling the same benchmarks as the previous year, high performance LinPack, HPCG, IO 500, which is great for us because the team already has experience working with these. This means that we can focus a lot more on the two new applications. So the first is Cardioid, which is a cardiac multi-scale simulation suite. This was developed at the Lawrence Livermore National Lab, as well as Quantum Espresso, an integrated suite of open source computer codes for electron structure modeling at nanoscale. And 2 members of the team have already been assigned to each of these, and we've already gotten started setting these up. Every year, the competition kind of likes to throw in a little curveball, keep things fun. Usually it's a power blackout, but this year they've decided to enforce a variable power limit that's going to change as the competition progresses. So these values are going to be between 2 to 4 kilowatts, which means that the team will need to be on the same page as to when we want to run our different applications and benchmarks, because each of them is going to require a different amount of resources. However, this also gives us an opportunity to overclock our system and squeeze out some better numbers where we might otherwise be lacking. So onto the architecture that we're proposing for the competition. For our hardware stack, we're going to run 2 nodes. Each one will consist of dual chip AMD EPYC Milans, as well as 4 NVIDIA A100s for a total of 8 GPUs in total, as well as 32 gigabytes of DDR4 RAM per socket. So that's going to be 64 gigabytes per node, and 128 gigabytes total. As well as they're going to be connected through InfiniBand, each of the nodes. For our software stack, we're doing something new this year with distributed file systems. I'll touch on that a bit later. And we're also going to be using some libraries and compilers that are going to help us by providing optimized support for our workload dependencies. So the AMD optimized C and C++ compiler, as well as the NVIDIA CUDA-X library are 2 of the ones that we identified. And an example of what these would have that would really help us is like linear algebra libraries, because a lot of the benchmarks and applications rely on those. So with regard to distributed file systems, last year, we didn't really focus on this at all. We just used whatever default came with the cluster that we built. However, we got a little inspired by the winner of last year's competition to explore some new options. And that led us to distributed file systems, specifically one type called local node storage burst buffers. One of the biggest advantage these offer over typical parallel file systems are that they have very little contention, or even no contention. and they also scale really well with nodes added. But of course, there are drawbacks. These file systems aren't so great when files need to be shared or when we're running producer-consumer applications such as CESM, which is a climate simulation model. Luckily, none of the applications this year fall into those categories, or so we think. So we should be in the clear for that. We're going to be taking a look at GeckoFS as well as UnifyFS. And Catherine Moore, one of the researchers who actually worked on UnifyFS, gave a pretty great presentation last year about some of the advantages it has over parallel file systems. So I just grabbed this from the YouTube video, and you can see that in the test that they ran, the parallel file systems, they saturate. They're hitting an upper limit as the number of nodes increase. However, for the UnifyFS is able to scale logarithmically with nodes added. So that we think is going to be pretty powerful. For our GPU, we're going with the NVIDIA A100. This SKU is the reigning champ for HPC applications. In comparison to the V100, we're going to be seeing lower per core clock speeds. However, we're going to get higher core counts, which is, of course, important for all those data parallel applications. As well, it's got more memory, higher memory bandwidth, and a faster memory clock speed, all that good stuff. And we plan to run HPL on our GPU stack instead of the CPU, which begs the question, why didn't we do this last year? Well, we tried, but we had some pretty significant problems with using Node and its scripts in Azure to get dependencies installed at runtime. But since this year we should have full control of our system, we expect this to be a much smoother process, and we'll be able to get better numbers for our benchmarks. So that's it for me. I'm going to hand it over to Harry, who's going to be discussing our CPU choice.
Great, thanks, Ben. Okay, so now I'm going to talk about the new Milan architecture and how it will help with our cluster's performance in the competition. So Elia mentioned some of these earlier today, but the Milan architecture comes with all the good stuff that the previous generation ROM has. And on top of it, it has up to 64 processor core per socket, improved CPU speed, and more. But the feature that we're most interested in is the L3 unified cache. So in the last generation, the ROM L3 cache boundary is every 4 cores and 16 megabytes in size. And now the Milan is every 8 cores and 32 megabytes in size. And we're going to see how this improves our performance from the recent benchmark result that we did in the next slide. Next slide, please. So before getting into the number, just a few quick notes about the HPL benchmark. The two most important parameters that you have to choose are the problem size and the block size. And if your block size is too small, the performance can be affected because you won't be reusing the data in your higher level cache. And you're also increasing the number of messages that's being sent through MPI. And to a much lesser extent, the problem size and the block size also has a correlation. So for example, if you find out that 44 is a good block size, it's possible that 88 gives you a slightly better result for a larger problem size because of higher flop rates, but that shouldn't cause a huge difference in terms of performance. So we ran, a couple days ago, we ran on various configurations, and the first one we did was with block size 192. The result was quite surprising to us because we thought the Milan would just come with a free increase in terms of performance. But actually, the result shows that with 192, it was almost the same as the ROM. So we were wondering why this had happened because the Milan is supposed to be a newer generation chip. And we looked into the important features and changes of the architecture. And as mentioned previously, we know that there's the new unified cache feature. And just a refresher, the ROM is every 4 cores and 60 megabytes for the cache boundary. And the Milan is every 8 cores and 32 megabytes. So on our lower level, physically speaking, the Milan has half as many blocks and 2 times as many cores and 2 times as much L3 caches. So that significantly decreases the probability of cache misses, which means that you get higher effective memory bandwidth. And in HPL, if your problem size is too small, not enough work is being performed on each of the CPU. So you can get like bad results and low efficiencies. And if your problem size is too large, it can cause swapping and the performance goes down. So we hypothesized that it has something to do with the scale of the problem size. That we're not utilizing the cache very well. So we turned up the block size to 224, and then we started to see an increase in the Milan. What really surprised us is that when we scaled the problem size to 100K, there was a significant boost, about 1.5 teraflops. And we're going to get back to this gap in a second after the next slide. Next slide, please. So just to see how far we can push it with 5 nodes and basic techniques, we were able to get about 10 teraflops with 200Ks in problem size. But interestingly, you can see that there is less of a gap between the Milan and the Rome, with a block size of 256. And we suspected that it was because previously the 224 was a bad alignment. So you get a lot of conflicts and capacity misses. But the unified cache compensates for that. And this is very good in real world applications because you expect to see a lot of bad alignment with your data. And so overall, the Rome and the Milan are both very good chips. And we're pretty happy to see that the Milan has an edge over Rome in real world applications. And we hope that this will give us an edge in the competition as well. Slide, please. And these are just some of the numbers that we got from all the benchmark we did. Yeah. So lastly, I just want to give a special thanks to our partners, and especially our advisor, Kurt. We couldn't have done any of these without them. And that wraps up for us. Are there any questions?
Did you run any benchmarks on Xeon-based platforms or in the cloud on Xeon?
We did it on Azure.
No. Yeah, so we didn't take a look at any of the Xeon SKUs. We were more focused on whether or not these Milan chips would be able to give us, better performance than what we saw last year. Because last year we used the Epic chips.
Gotcha. Thanks.
So Howie, do you think if we selected a SKU that had a larger cache, we could also fix some of the differences between what you're seeing on the Rome and the Milan?
Mm-hmm. Yeah, definitely. I mean, we have to do more testing, but I think so.
Okay.
So nice presentation. I'm just wondering, so you're doing the virtual competition, not the physical one?
No, we do hope to do an in-person competition. It seems like you already know that for this year, there's 2 choices. Teams can choose to select in-person or virtual. We're going to just submit to both, and whatever they give us, we will gladly take. Our hope is that's going to be in person. And the reason we did all this Azure testing, is because Microsoft was the first to get these Milan chips. They're not going to be out for regular purchasing until November, I believe. But we have access to them through Azure, so we wanted to get a quick first peek at that.
And is Microwave your sponsor and going to provide you with your system?
Yep, that is the hope.
It won't have any GPUs in it, though.
Yeah, that might be a little.
We don't have to have any GPUs. NVIDIA will provide those, right?
Well, yeah, that's what I'm saying. I don't think NVIDIA's going to offer that deal to the students this year.
I don't think they're going to give them A100s. No.
Yeah.
I think you should be planning on B100s.
Mm-hmm. Yeah, we've got some time before the final.
This is Dave Kelly. I've mentored the team a number of years.
Right.
Yeah. But it's great you guys are going forward, and kudos to you for putting this together. I think you've got a great team, and I think you'll be very successful. If we can give you any help, last year we did better on a number of the applications. So if those students are available, and would be happy to talk to you.
Okay, that would be great. Absolutely, yeah.
Dave, what did your VMs look like on Azure? Were you also?
Oh my God, I forget. Come on, you gotta be kidding me.
You were Epic based though, right?
Yes.
Okay.
I think everyone can send me their slides for the Blue website.
No problem.
How should we send ours to you?
My address is jabr@blu.org.
Okay.
Thanks.
I know they always quiz you about the apps. What is the use case of Cartoid?
I think currently it's just to do simulation for cardiac mechanics. We haven't delved too deeply into that yet.
Cool.
They said on the Student Cluster Contest.us site that there was a CUDA implementation of it. So that means, and of course, Quantum Espresso has had NVIDIA support for a long time. So that's definitely pushing us towards NVIDIA for those two codes. And we don't know what the mystery app's going to be, but that's all the 3 benchmarks and the 3 application codes. Is that everything? Is there going to be a repeatability test this year, Ben?
Yeah, there will be.
Okay.
Reproducibility, that's a given.
Reproduce, yeah. Okay. So what would be neat is, because they've stuck this 2,000 watt to 4,000 watt experiment in this year, is if we had user land access to the BIOS and could change things ad hoc on the fly, possibly without rebooting. I know with at least one of the Dell systems, you can get 160 lanes of PCI Express on one of their systems. Mm-hmm. So it'd be great if we could say we had both GPUs in there and a ton of other things on the PCI bus, like NVMe or accelerators or something like that. We could, in situ, change it from an IO-centric device to a GPU-centric device, possibly without rebooting, maybe warm rebooting. Isn't that true, Elliot? We could do if we had.
Now, what you can't change, in my experience, is the CPUs. So you, like if you've got an AMD EPYC CPU, they do have configurable TDPs, but that requires a reboot. Actually, I didn't mention this in my presentation, but Intel has some things called Speed Select that do not require a reboot if you have a modern OS, which is going to be interesting. You can turn off cores, supposedly. But you can go into the BMC. So you can go into the system BMC and mess with the fan settings. These days, the fans on a server are not usually controlled by the BIOS. They are controlled by the baseboard management controller. It's usually an IPMI device. So you could change the fan settings, and the fans can use a few hundred watts on a GPU system. And then the GPUs themselves, if it's an NVIDIA GPU, you can toggle different power settings within the operating system with NVIDIA.
You can do that on AMD GPUs.
Okay.
Yeah, we actually have a corruption of AES by doing that.
Oh.
We presented that paper today. It's crazy. It's all via public interface. No on real hardware.
Wow.
Can you tie some of this functionality to like top or HTOP or something and start killing off processors if you hit 4,000 watts? That would seem to be the usage case, right?
Most servers do tell you their power consumption via the IPMI controller. So you could query the IPMI controller, ask how many watts are in usage, and then make a decision based on that. You can also give, I don't know as many specifics about the AMD GPUs, but the GPUs consume the most power and seem to be the most configurable. So I think that's where you focus your efforts.
Yeah, there is complete configurability on the AMDs, but you're not going to use AMD.
So you can set a power threshold. You could play it kind of ahead of the competition. You could look at what your wattages are and which different power thresholds you want to set.
Yeah.
How much potential power savings are you looking at an NVIDIA GPU by doing this?
If you're talking the V100, it can peak between 250 and 300 watts, and you can set it all the way down to 150 watts. So almost a 50% reduction.
No, but an idling NVIDIA GPU doesn't consume 250 watts.
Oh, that's true. Okay, so if you're idling it intentionally, it will be very low, probably I don't know what, 10 to 40 watts. But if you're actually using it, you usually can't set the threshold lower than 150 watts. And I don't know why that limit is in place, but if you're using the GPU, you're not going to be able to use it at 60 watts or 100 watts. It's going to have to be 150 watts or higher.
Got it.
You could use fewer GPUs though, if you needed to be somewhere in between.
From past experiences, it is always helpful to use more GPUs underclocked to get good performance.
Yeah. Okay. Yeah. I guess you'll have to see if you can get all of your GPUs at 150 watts each. So that's kind of the floor on the power threshold.
Makes sense.
Consumption does depend a lot on your workload, though. We've seen that quite a bit.
You'll win the competition just for being cool if you can tie this to a speed pedal and be able to like step on the speed pedal and speed up the device, the clock. So, come up with something innovative there.
Well, to Kurt's reference at Spinal Tap, I think you have to go to 11, right?
There you go.
Yeah. Well, if they let us go to 4,000 watts, that'll be a first. I mean, we've never been able to do 4,000 watts at the student cluster contest.
I would say that it's a fairly doable project to have a shell script that is querying the server power consumption and adjusting the GPU power usage based on that.
Yeah.
The problem is it doesn't always. It depends on how close you want to get to 3,000. There is a delay between what you do with the shell script and how much it actually consumes. And every time you go above that 3,000 limit, it starts ringing, and you get penalized for that.
Trust me, Crosstop's tried everything.
Oh, Elliot, can you unclick follow me? Because on the YouTube, I just have your screen. And I'd like to see the tau mode since we're in a discussion right now.
Is that inside of Jitsi?
Yeah.
Oh, okay. I'll find it.
Yeah.
If you go to the three dots.
Either in the three dots or just unshare.
Yeah.
So if they're going to start allowing us to go to 4,000 watts, this cluster competition is rapidly going to become a server competition, because who wants to waste 150 watts on a network card when we can just overclock every GPU that's in a single server? Especially if we can get another 100 watts into each of those GPUs, that'll get us to 3,000 or 4,000 watts pretty quick in a single server. 4P server.
Yeah, I've always wanted them to make this about programming, and they never want to make it about programming. They want to make it about system administration.
Yep.
And I totally disagree with that.
Elliot, were the wattages on those Bluefield cards?
Oh, that's a good question. I don't actually know off the top of my head. I'm guessing it's likely 150 watts. You could probably get them by competition time, but I don't know what availability in general is going to look like. Oh, and Jerry, Jitsi was giving me a warning message. I might just have to jump out and back in because it's not giving me that option.
Okay.
Hey, Ben, will they have the unplanned power outage test this year?
No, not for this year.
Okay.
That's what the variable power limit is for, is replacing.
Okay.
Yeah, that was ridiculous.
Yeah, not too many schools turned on their system and had everything come back after those.
Variable power is just replacing the binary state power with a floating point number.
We tried to game that one year. We had a couple of students watching for the guy who was in charge of grading the power outage contest. And when he saw him, he would call the other team on a cell phone and said, "Hey, he's coming into the student cluster contest area. do a quick checkpoint restart or checkpoint. So it was kind of tough to game that challenge, but lots of checkpoints. Only one restart.
Looks like Elliot's back.
Hey there.
So, Elliot, do you think your company will have a booth at Supercomputing this year?
Yes, in some capacity, definitely.
Yeah.
We know contractually we are participating, but what I remember from last year is that I don't think they decided on the final format until fairly late in the year in the fall. They didn't go all remote earlier in the year. They kind of waited. So I'm anticipating something like that again this time. We might not know exactly what it's going to look like until October.
Yep.
Yeah. And Elliot, we're doing something through MGH-PCC, and we definitely do want microwave highlighted with the AI Jumpstart work. So
yeah, that'd be great.
Okay.
I think this is the first year it's been in St. Louis. I wonder what the crowd will be like.
Yeah, center of the country. I mean, maybe it's good for U.S. attendance. I don't know about international attendance this year.
You said that's going to be in November?
Not my favorite city.
It's I think it's a week before Thanksgiving. Yeah, in November.
Yeah, so weather will be an issue too. Anyway.
Hopefully by then everyone will be vaccinated.
Yeah, I just got my appointment this week. I'm excited.
Yeah, I hope other people. I've had my two. I know Jabber's had his too. So.
Yeah, I got my second one on April 5th. So I'm in the clear now.
Yeah. Yeah, but my wife has hers, and my daughter and my son-in-law both have had their first.
I've had my second, but not a full 2 weeks yet.
Okay. No side effects?
Enough side effect to convince me it was working, but not drastic.
Yeah.
Yeah, the only side effect I had was my arm was sore for a few days, starting like 2 days after I got the shots.
I did not have any pain in my arm at all.
It only hurt when I touched it.
Yeah, in my case.
So MIT is going to do a data center challenge. I'm going to stick the link into the chat. This is still very much a work in progress, but I think they'll have the bulk of the website together by next week or the week after. Should be interesting. I know they're looking at a lot of the benchmarks that are interesting to Lincoln Labs and MIT, including the HPEC challenge. Yeah, let me dig up the URL for the HPEC challenge. HPEC challenge is a little bit like the HPC challenge. See if I have the.
So do we want to sink a container in Boston Harbor for the free cooling like Microsoft did in Scotland?
I like that. Except it might, might get stuck on some of Whitey's old friends.
In shopping carts, yeah.
Yeah.
How did that experiment work out for Microsoft? Did it consider it a success?
Apparently so. It continued working until they recovered it to inspect it.
So, Kurt, what's the deal with this data center challenge?
So this is the 25th year of HPEC. So they wanted to have a remote challenge of some variety, and I think they talked to some folks about, they've tried to do the HPEC challenge before, and there's only a few interesting things there for vendors. NVIDIA was very interested in the synthetic aperture radar for a while, but otherwise the HPEC challenge hasn't really taken off. So I think they're going to try to put this data center challenge together. And you know, that description there is a little thin, but I think if you check that website in a week or two, it'll be in better shape.
But who's it targeted at? Students? I hope.
I'm trying to think what they. Let me find out what resources they're going to make available for this. I thought it was going to be part of Satori, but that wouldn't make sense. They're really not. Do they mention Satori here? Yeah, they don't. So let me find out what resources are available, because that would probably define it right there. If it was if it was one of the MGH PCC clusters, then it would definitely be a student competition, right?
Well, I mean, you have the students build their own cluster if it's constrained somehow. It doesn't cost them an arm and a leg. I mean, we were trying to do something like this a year ago for sort of a Boston, cluster competition, and we just didn't get enough interest from other universities.
Yeah. Yeah, there's no, okay, I read through the verbiage again. There's no nuance that tells us whether this is a really big data center challenge or a really small data center challenge. So let me do some research on this.
Okay, great.
Well, I don't think we have anything more, Jerry.
No, I think that's about it.
Next month, so I just got an email from Seed Studios about my Beagle 5 coming in the mail. Did anybody else apply for a free Beagle 5? So Beagle 5 is the first RISC-V based Beagle board. And it's going to be interesting to see if we can do anything. It's a 64 RV64. So ostensibly we'll be able to run some HPC level libraries and operating systems on it. But go to the BeagleBoard site and see if you can register for one of these. They're giving them out to academics to do beta development on, and I think they'll probably be in general supply. You'll be able to buy them from Seed Studios in November. But see if you can get in on the beta test. It'll be interesting to see how well they work relative to their expensive cousin from Sci-5. And next month, of course, is the SBC roundup. So we'll get a bunch of Beagle board and Panda board and Eagle board and Ram board people to come and talk about their SBC experiences. I think we'll have a couple of Texas Instruments speakers next month, Jabber. So I'll get their bios to you.
Yeah, I'm curious. Do any of those have both Gigabit Ethernet and SATA?
That card, the Beagle 5 card, you mean?
Yeah.
No, it has Ethernet but not SATA. So I should have mine next week. So I'll give you Bill Ricker has advised me against this, but I'll give you guys all remote access to it. So I mean, what's the worst that can happen?
You might have to unplug it and plug it back in again.
Take a backup before you let everybody in.
Yeah, folks. So if you have a single board computer or a dev board or something you'd like to talk on next month, feel free to come. I've got a ton of Panda boards, so I'm going to talk on the Panda board, which I just loved it when it came out, and I still have some use for it. It's very interesting, some of the feature sets that they built into that board. And I'll see if I can dig up. I had one of all the early Texas Instrument boards that were named after animals, so I'll see if I can put a little quick video together of that.
Hey, sounds good.
I got a Panda board as well, but this one is from, I don't know if you've heard of Comma 2. It's a AI startup that converts your car into a self-driving car. It uses Panda board, and I ordered one of those. So I want to play around with that.
Oh yeah. And the BU team will probably know by the third week of May whether we're accepted or not. We don't have to send the paperwork in until May 1. I mean, well, that's the deadline, but we should probably hear back, I would think, 3 weeks after May 1. That sounds like about, does that sound about right, Ben? Do we hear back in May whether we got accepted or not?
Yep. I think it's actually mid-May, pretty soon after we
Okay,
submit.
good.
Might not even be 2 weeks.
Alrighty. Well, Kaustub, we'll pick your brain on how to run HIP. We may have to go out and find other GPUs and run our CUDA codes on HIP.
Yeah, sure. Yeah, sure.
All right. Well, thanks, guys.
Thank you, Kurt.
Take care.
Thanks,
Thanks,
Elliot.
everybody. Sure.
Thanks, Ben.
Thank you, everyone.
Everybody.
Thanks.
Thanks.